Welcome. Mini-Science for 2021 begins tonight. This is our bicentennial series. Every month, we will be bringing you presentations by leading McGill scientists, and they're going to reset the future for us. This is our chance to join them. We are all located together on the traditional territory of the Haudenosaunee and the Anishinaabe nations. McGill respects, honors, and acknowledges these nations as the traditional custodians of the lands and waters on which we work, meet, live, and exchange information together. If you're not from the Montreal area, which is where we are all from, McGill University is located in Montreal, Canada, I encourage you to check out the website native-land.ca. Lots of information that you can explore about territories, cultural groups, nations, language groups. Tonight's speaker will be introduced by our student ambassadors, Anthony Pannunzio and Tiffany Chénier. The student ambassadors have been assigned to a speaker each month. Not only are they introducing her, they will also be conducting the chat after her presentation. There have been questions posted to us in advance. We will pose all those questions to Doina. And then I will close at the very end and tell you what to stay tuned for next month. Anthony and Tiffany, please introduce our speaker for this evening's special presentation.
All right. So hello, everyone. My name is Anthony. I'm joined by my colleague, Tiffany. And tonight we're going to be presenting Professor Doina Precup. She's a Romanian researcher who specializes in artificial intelligence. She completed an MA in science at the University of Cluj-Napoca in 1995, followed by an MA and PhD at the University of Massachusetts Amherst in 1997 and 2000, respectively. She currently leads the DeepMind office in Montreal, a project spearheaded by Google.
She is also currently conducting research on reinforcement learning at DeepMind, analyzing how AI applications can have a social impact in fields such as healthcare. She's also a senior fellow of the Canadian Institute for Advanced Research, a fellow of the Association for the Advancement of Artificial Intelligence, and a member of the Montreal Institute for Learning Algorithms. She is also involved in correcting the gender imbalance within the discipline and is the co-founder and advisor of the AI for Good Lab, an organization which aims to enlist more women in the field of artificial intelligence. And now she'll present to you Artificial Intelligence and the Age of Reason.
Hello, everybody. It's really a delight to be here to be able to share with you ideas about artificial intelligence. Thank you very much both for the invitation and for the kind introduction. The title of my talk tonight is Artificial Intelligence and the Future of Reason. And really what I want to tell you about is what is AI and how do we get from the sort of science fiction idea of AI, of robots who are helping people do various tasks or are sometimes very much like people, all the way to the reality of AI applications that we have today. I started studying artificial intelligence actually back when I was a university student. I was very interested in sci-fi at the time, and I wanted to build androids like Data. That was one of my dreams. We are still kind of far from that dream, but we have made really great strides in the last little while. Of course, you all know that cars are now able to drive themselves pretty well, far from perfectly, but still we've made great progress there. We all have intelligent assistants in our phones that we can talk to, and they can help with various tasks like scheduling things and finding information for us. All of this is due to a revolution that is driven by AI that is in some ways similar to the Industrial Revolution that we had seen back in the 1800s. Back then, machines were used to extend humans' mechanical power with the invention of the steam engine. And while that caused at the time a lot of fright in terms of the jobs that would be lost, in the end it led to great progress and many more jobs being created, and of course a big transformation both in the workplace and in society. The AI revolution is ongoing, and it promises to transform the world in terms of enhancing humans' cognitive power rather than their physical abilities. And we anticipate that this will in fact affect all sectors of the economy and improve our lives in dramatic ways. This is the goal that we are working towards. AI is really a collection of sub-disciplines, and a lot of the recent progress has been driven by machine learning, which is the linchpin of current AI research. Why is this happening now in the last couple of decades? Well, really, the key ingredient in all of this is an explosion of both data, devices, and computation. You have two pictures on the slide. One is showing the computational capacity of devices. It's a log scale. And so really what it means is that the computational capacity is per dollar is actually increasing exponentially. And in fact, if you have a cell phone today, you're carrying in your pocket more computation than the amount that has taken us to the moon back in the 60s. At the same time, there are many devices that are connected to the internet, specifically through the Internet of Things. This includes microscopes, this includes monitoring devices in hospitals, cardiorespiratory monitors. It includes devices on manufacturing floors. It includes video cameras in our phones and data that we produce on the internet. And so the amount of data has been exploding. And really, this is, in some sense, a perfect situation for machine learning algorithms, because on one hand, they have a lot of information on which to train. On the other hand, there is a lot of need for them to come in and help us make sense of this massive data. And the computational power that is necessary is available to almost everybody. I'm going to tell you a little bit about the different kinds of machine learning in order to make it a little more concrete what AI systems actually do. A lot of what is used today in industrial applications as well as other kind of applications is what we call supervised learning. Supervised learning means that people have access to data which has been labeled by some experts. In this case, the data is some images. And if we're interested, let's say, in trying to identify faces in these images, we will have somebody label faces. And so in this particular case, we have three people in the image, and there are some squares around their faces that were drawn by some other person. And in this case, the task is easy to perform by many people. The goal is then to find a function, a way of mapping new images to a desired output. And so, for example, in this case, we might want to obtain a system that says, yes, this image contains people, it contains 3 people, and perhaps even is able to locate exactly where in the image their faces are. So for this, we need an expert, somebody who labels the data. And given this, we can then train a learning algorithm to find this mapping, which can then be utilized on new images that have not been experienced before. At the core of recent developments in this field is a technology called deep learning. Deep learning, intuitively speaking, has to do with trying to construct complex functions out of very simple elements. The intuition is very similar to the way that the human brain works. The human brain is a very large collection of very simple neurons. Each neuron by itself doesn't do very much, but the connections between them can help them carry out a lot of information and do very complex processing. And so similarly in deep learning, we have collections of artificial neurons. These are very simple computational units that usually do some sums of their inputs multiplied by some weights, and then sometimes they introduce a threshold. And so each of these units by itself is very simple, but when connected together, they can accomplish very complex tasks. And a lot of the power is in these weights, the numbers that are on each of these little lines in the picture. These weights are trained in order for this function to be able to match the desired output on training data. And we can, in fact, look inside one of these models. The picture here depicts what's called the convolutional neural network. This is a standard way of analyzing images. And we can look at activations of these different simple units to try and understand what they do. And so oftentimes in these models, what you will see is that you have some units in the early layers that are a little bit like cells in the visual human cortex. they're sensitive to lines and different orientations, and so they will light up if a line in that orientation is present in the image. In this case, if we're training the network to do face recognition, we might also find some nodes that are in the later layers that light up when there's a face in the image. And then we might also find some nodes that do some different interesting things. So for example, in this case, you can see here a node that is a cat node. It lights up whenever there's a cat in the image. Now, this is not a task for which this network has been trained. It's supposed to focus on people, not on cats. However, because this is trained with data from the internet, where there is a lot of cat pictures, some of these neurons will latch onto the structure in the data. And so this makes an interesting point. These models are really competent if the data that they are fed are good. And if the data has problems, these models might actually latch onto those problems and reflect them. And so this is one of the fundamental dilemmas in machine learning. How do we ensure that our models are ingesting the right kind of data, and as a side effect, they do not produce spurious results or even worse, results that are actually malicious or biased in some way. Now, what's the deep part of this model? Deep refers to the number of layers, which has been growing quite a bit over time. Neural networks have been around since the 80s, but one of the big advances recently has been our ability to be able to build bigger and bigger models with more and more layers and train these in a stable way. Deep learning has led to a revolution in many tasks that were considered traditionally very difficult for automated systems. For example, image recognition. This is an example from a data set called ImageNet, which was produced about 10 years ago. It has many images with more than 1,000 object categories. Deep learning models have been trained on this data set for a long time. And since 2015, they are capable of achieving human-level performance in these tasks of labeling images, identifying objects in images, and so on. Why do they do so well now? Really, the main algorithmic ideas are actually pretty old, but one of the things that we have learned is to scale these models. And so we have now more powerful computational units called graphic processing units, which initially were developed for video games, but they have now been repurposed for machine learning. We have much more data in our data sets than we had before, and we have learned some tricks to stabilize the training of these models and to really be able to scale it up. There are many practical applications. In fact, this is a slide that's taken from a recent Nature review paper that looked at applications of deep learning, convolutional neural networks in medical imaging for a whole host of classification problems like localizing carcinomas, typing lymphomas, segmenting tubules in cellular images, and so on. In all of these cases, we rely on data sets that are labeled by people. But we also have learned to leverage either data that is unlabeled or data that is labeled for other purposes or for other diseases in order to grow our data sets and therefore to be able to build bigger and more interesting models. In a lot of these cases, machine learning, these deep models, have basically replaced more traditional ways of doing feature extraction with results that are beneficial in terms of the accuracy of the predictions that can be obtained. We don't just know how to label images, we also now know how to generate images. So some of these models can be sort of turned on their head, so to speak, and made to generate, for example, faces or other kinds of objects. This is a picture that depicts the quality of faces generated by deep learning models from 2014 on the side of your screen all the way to 2020. You can see that at the beginning, these were sort of faces, but very blurry, had all kinds of imperfections. And now these models actually have become quite powerful and able to do really good generation. Now, on one hand, of course, this is very exciting. This tells us that these models would be able, for example, to fill in missing data in complex data sets. At the same time, this has also led to a problem of deep fakes, right? Generated videos and photos that are not real, and that, you know, now we have to contend with and be able to remove. So like any technology, AI has its positives and its negatives, and going forward, part of what we need to figure out is how to use the technology properly and to prevent its negative side effects. Another place where deep learning has revolutionized existing systems was speech recognition. You might have noticed, if you have, again, a mobile phone, that you can talk to the phone and its ability to recognize what you say has drastically improved in the last little while. This is because we now have deep learning models that can take in the sounds, the sound wave that you're producing, and parse it into words and be able to recognize what you are saying. And so this is a graph that's showing error rates, and you can see the error rates dramatically dipping after these technologies have been introduced. This is a little bit of a different example. It's a very recent success story from DeepMind, which is my other employer aside from McGill University. This is a system called AlphaFold, which was developed by my colleagues in the science team led by John Jumper. The system learns how to produce 3D structures of proteins from a string that describes the amino acids that are present in that protein. Now, in biology, this is a very important problem because knowing the 3D structure of proteins means that we can also find, for example, targets that bind to them, so we can develop drugs more easily, and also we can understand many things about life a lot better. So because of this, for a long time, there was a competition that was organized in the biology community called CASP. And the picture on the bottom, the bar graph, is showing the performance of systems that were entered in the CASP competition over the last 15 years or so. Many of these systems originally were based on a lot of biological intuitions that people had. The last couple of years were dominated by AlphaFold, which has now reached a level of performance that was not believed to be possible in the biology community, and which is really quite extraordinary in terms of the precision of these predictions. The way that this was achieved was actually by training on databases where we know the sequence of the protein, we know the 3D structure because it has been determined by, for example, X-ray crystallography or some other method like this. And so we can train deep neural networks in order to predict from a string what the structure might be. These neural networks have a little bit different structure than what I showed you before. The structure does take into account the fact that we have to work with proteins. They're trained to predict two things. One is how far away in space two amino acids might be in this 3D structure. The other one is to predict the links of different bonds. And then the training happens by a method called gradient descent, which is sort of the bread and butter of deep learning. And at the end, we produce a three-dimensional structure of the protein. The bigger picture that you see there is the ORF2 protein, which is one of the proteins associated with COVID-19. This was made available publicly last summer when AlphaFold was able to actually make these predictions for several of the COVID-19 proteins in order to sort of facilitate perhaps the development of drugs for this disease in the future. Now, we talked a lot about supervised learning. Supervised learning relies on data being available with labels, right? So in the case of proteins, we need to have the string of amino acids and the correct 3D structure for many proteins in order to be able to train. But sometimes we don't have labels available, yet we have data available. So in the picture that you see there, for example, these are some trajectories that were taken from an accelerometer. That's the accelerometer in my phone. And you can see that these trajectories are periodic. You can see that one of the bunches has spikes in it, the other one does not. We could sort of ask a machine learning algorithm, can you do something with this data? Can you learn some interesting structure that is present in the data? Okay, so the goal is to find some interesting patterns. Now, this is a little bit of a hard problem because there's not necessarily a single correct answer. So for example, it might be interesting that in both of these cases, the data is periodic, or it might be interesting that in one case we have the spikes and in the other we don't. Turns out that the spiky data is actually taken from jogging, whereas the other one is taken from biking. Nonetheless, unsupervised learning has also made quite great strides in recent years. This has culminated last year with the development of GPT-3 by OpenAI and then some related models. These models rely on reams of text that is available on the internet. And what they do is they train deep neural networks to predict the next word in a sentence based on previous words in a sentence. Now, one of the innovations that was brought by GPT-3 is actually to leverage not just simple text data like this, where you can predict the next words, but actually data where you can do translation, maybe because you have both, let's say English and French on the same page. Also to leverage data that contains more structure, for example, additions. And so each of these, it's considered a task. Each of the blue rectangles in the picture is basically a task. And we can ask a model to train across all of these tasks to try and do predictions correctly for all of them. In none of these tasks do we actually have a ground truth, but in all of these cases, the system can train to reproduce what is there next in the data. And so this actually leads to a really powerful model, which is a gigantic neural network. It's recurrent. This means that there are some connections that feed back to previous layers. And it can do a lot of interesting things, including text generation of various forms, doing dialogue, generating news. It can generate computer code, do some mathematical proofs, fairly rudimentary, but still it's kind of interesting. And even it can generate images. And so, for example, in the picture here, you see some images that are obtained by one of these types of models. If we feed it the phrase, a chair shaped like an avocado, and so you can see that it generates all kinds of images that look like chairs that are kind of shaped like an avocado. This opens up the possibility of using these kinds of tools as a creative aid, right, for artists and for other people who perhaps need some kind of inspiration or support in their creative process. Now, my own research is in a field called reinforcement learning, and reinforcement learning sits somewhere in between supervised and unsupervised learning. And in fact, the reason why I became very interested in reinforcement learning is that it's inspired by some of the animal learning theory and some of the cognitive science learning theory that has existed before. So in supervised learning, we require labeled data. This means that we need to have an oracle, somebody who's very smart who gives the right answers in this data. In unsupervised learning, we just have reams of data. We can do some very interesting things, but there are two problems. One is that the system is sort of uncontrolled, and so therefore it can produce results that are not meaningful for any particular task. And second of all, it's actually quite hard to get unsupervised learning to work reliably. So even a system like GPT-3, if you ask it to generate text using the same prompt, it might give you some really good pieces of text and some really garbage pieces of text. Reinforcement learning aims to guide an AI agent to do a little bit better. And it assumes that this agent has the ability to interact with an environment, and it essentially drives the agent through rewards, just like you would with, let's say, pets or children. A reward is typically a positive or a negative number. And the bias that we put in the system is that it wants to maximize the total reward that it receives over a period of time. And so, this goes back to animal learning theory, where in order to train an animal to perform a task, you might offer a food reward. And so in the picture there, you see a little mouse who is learning to press a sequence of levers. And of course, we can't tell the mouse the right sequence. The mouse needs to interact with the levers in order to understand what it needs to do. Whenever it does the right thing, it receives a pellet of food. That's its reward. And it turns out that animals are really good at learning to optimize these rewards, even though the rewards come at a delay after the right action has been performed. In the other picture, you see an automated agent that is trying to learn in the same way. It's in an environment. It perceives the state of that environment through its sensors. Could be cameras, tactile sensors, words, and so on. It can choose actions in that environment. For example, if you have a robot, the robot might decide to move around or to move its arm. And it receives rewards, positive and negative numbers, and it learns over time to maximize the sum of rewards. There are some interesting aspects to this. First of all, the learning is by trial and error. The agent needs to actually do things in the environment in order to understand what's the right thing. Reward often comes delayed, as we mentioned before, and so agents need to perform a trade-off between exploring, trying out new things, and exploiting their knowledge, trying to do actions that they believe to be good based on their past experience. One example that happened in 2016, a very successful reinforcement learning program, was AlphaGo, again, elaborated at DeepMind. This was before the time that I actually joined. And it was one of the surprising and very exciting successes in the field. AlphaGo is a system that learns to play the game of Go using deep neural networks, reinforcement learning, and search. And in the picture there, you see my colleague David Silver, who's actually trained in Canada, receiving the award on behalf of AlphaGo as being a Go Grandmaster. A lot of this work actually was performed by former students, both from McGill and elsewhere in Canada, and quite a few of them actually have now returned to Canada, which is really good news for us. So how do AlphaGo and similar systems work? Well, their perception of the task is the state of the board. In this case, the board contains white and black pieces and is a finite 18 by 18 square. So we can encode this for the agent as an image. The actions are legal moves in the game. And the reward is only obtained at the end of the game. And at the end of the game, the agent gets either a +1 if it's won or a -1 if it's lost the game. And that's all. We otherwise don't tell the agent what are good moves or bad moves. There is no other heuristics that are involved. It's just the reward based on the wins and the losses. Now, in order to train, the agent needs to be able to experiment. That means play games against an opponent. And because these systems require lots of data, we need to play millions and millions of games. And so how does an agent get access to this? Well, the way that this particular system works is that it trains by playing games against itself. Its own strategy is randomized. It has some noise in terms of the actions that it chooses in order to explore. And because it plays against itself, it can generate a tremendous amount of experience and train from this experience. Now, what does it train exactly? Well, in this particular case, there are two deep neural networks inside of the agent's head, so to speak. One of them, which we call the policy network, learns to map the board state into a probability distribution over actions. So this means, with what chance do I want to choose among each of the legal moves? The other construct that we train is a value network. And the value network tries to estimate the probability of the agent winning from the current board position. And this probability of winning is going to guide the agent in its choices of action. It's going to help train the way in which it chooses actions. Specifically, the agent tries more and more over time to choose actions for which the states that it gets to have a high probability of winning from there on. Interestingly, because this agent is trained by playing against itself, not from human data, it can invent new ways of playing which seem superior to the ways in which people play. And so this is actually, for me, really exciting because it means that AI agents can in fact go beyond the capability of people, at least in some respects. It can also seem a little bit daunting, of course, because it means that we will need to be able to understand their limits and also convey through the reward function and through the environment constraints, what do we expect from these agents? One example, concrete application of these kinds of methods that we're working on right now at MILA, the Quebec AI Institute, is actually drug discovery. Specifically, we have a project called Lambda-Zero, which aims to do a very vast search through the space of molecules. Now, why do we want to do this? It turns out that whenever people do drug discovery now, they can only look at a very small fraction of the entire space of possible molecules, the small gray circle that you see in the picture. This is because a lot of the search involves running very complex physical simulations or doing chemistry experiments. Of course, the physical simulations can be run in a computer and so can be run much faster than an actual experiment in a chemistry or biology lab. However, even these simulations take many, many days to complete. So what we aim to do is to train a learning system so that given a target, let's say a protein that we want to, to bind to, it can do a search in the space of molecules where the current perception is a particular molecule and the actions are adding things to this molecule, a little bit like Lego blocks. And as the agent moves around in the space of molecules, it has a neural network which is trained to estimate what would be the binding affinity or the energy, the binding energy of this particular molecule to the target that we're interested in. And we're going to try and direct the agent, reward it for finding molecules that have a favorable binding energy. And of course, this is a vast randomized search. We train it based on existing physical simulations, but we hope, just like in the case of AlphaGo, that the system will, in the end, through trial and error, be able to find a much better strategy for searching the space of molecules. And as a side effect, we hope to be able to search in a space that is 10 to the power 18 molecules, so an exascale space of molecules. That would be very exciting because many unknown drugs and materials may lie in this space, and we hope to be able to find it using these techniques. Another aspect that I'm really interested in is something that perhaps would seem less exciting and less intelligent, but turns out to be quite interesting and complicated. Can a robot actually learn to cook you dinner? Now, I'm sure some of you are getting hungry since it's getting close to dinner time. Imagine that you had a robot in your kitchen that would already be able to have the dinner on the table when the stock is done. That would be really amazing. It would be very amazing for me because I have 3 kids and a husband, and so dinner and who cooks it is always a big question. In order to do this, however, even going beyond hardware limitations, we have a lot of challenges that we need to tackle that are not able, that our AI systems are not able to do right now. For example, there needs to be reasoning at multiple levels of temporal abstraction. Some of the actions that are required take a long time, like planning a recipe, which might need to be done a couple of days ahead of time. Some of them are medium scale, let's say, like boiling something for 10 minutes. And some of them are very fine grained, like stirring the pot while something is boiling. And all of these actions need to be interleaved and decisions need to be made at all of these levels of abstraction. And some of these decisions may need to be reactive. If the cat gets on the table, for example, and spills the pot, something needs to be done to fix that situation that was perhaps not foreseen. This requires understanding the role of objects and how they interact with each other. It requires making predictions about all kinds of things over many different durations. And these predictions need to be grounded in observations. It requires learning about cause and effect. For example, understanding that if something has been left to boil for too long, the pot is going to be damaged. Cause and effect is one of the frontiers currently in AI. A lot of the systems that I've been telling you about are actually systems that learn to make predictions by looking at correlations in the data, but not really understanding causal relationships in the data. And so that's one of the things that we are working on with some of my students as well. In terms of applications, there's actually a lot of potential in many different fields. This is a very busy picture that I took from a US recent report that came out in February. about the AI and the way in which it drives innovation, as well as the threats that it may cause. And as an engine for innovation, you can imagine it making a huge impact from healthcare, where it might help us keep seniors in their homes for longer by using smart sensing capabilities, monitoring patients in the ICU, allowing better sort of clinical trial structures, drug discovery, which I talked about a little bit. There's many applications in education, for example, remote digital tutors that can help students come up to speed, even if they're behind. There are smart city applications that are being thought about and being developed that use sensing capabilities on roads and bridges in order to coordinate traffic, for example. And of course, there's always space exploration, which I think you'll also hear about in the next mini-science talk. So there's a lot of possibilities of applications, but there are also some challenges, some interesting challenges in our field. One of the things that I'm quite passionate about and I would like to be able to handle is the problem of imbalance in the research community in the AI field. AI is a cutting-edge technology, and as a side effect of that, it really needs to be inclusive. We need to have all of the people who will be impacted by this technology at the table to be discussing its uses, to be discussing its potential, and to generate ideas for new things that we could do. However, only 13.5% of those working in machine learning currently are actually women. And visible minorities are also very drastically underrepresented in our field. And we really hope to improve this, to diversify the AI workforce in order to be able to be more creative and also to spot problems, right? Like bias, for example. One of the approaches that I've been using is actually to try and find non-traditional ways to reach people who I think would really enjoy being part of the AI community and who can really help us think also in non-traditional ways. This was the reason why in 2017, I started with Angelique Manella, who was Associate VP Research at McGill at the time, an enterprise called the AI for Good Lab. This is a summer program, a 7-week program that brings in 30 women, undergraduate and sort of junior graduate students who are not necessarily from a computer science background. And we spend the first few weeks talking about machine learning and teaching them about machine learning algorithms. And then they work on a project. And this project is an AI for Good project. And so it's often geared towards solving some interesting, important, practical problem that machine learning tools or AI could be applied to. And so one example is this company, mini startup that came out of this lab called Bicentennial AI. This was a team of 4 women who wanted to identify bias in text and propose alternative phrasings that would remove that bias. And so that's actually still ongoing. The program this year is actually expanding to be both in Montreal as well as in Edmonton. It's virtually because of COVID, but still we are very excited to actually receive a double cohort. And one of the important things for this program is that actually not only it's free, but we are able through industry sponsorships to pay a stipend to the participants so that they don't have to sacrifice, for example, summer jobs or internships in order to participate. This is just like having a mini internship, but where you're also learning useful skills. Now, what's the future? One important aspect that I want to emphasize is that AI is not here to replace people. AI is here to help people. It is a tool, just like a hammer or a tractor, right? It might be a more interesting, a smarter tool, but nonetheless, it needs to be used by people and to work together with people, with humans in the loop. And this brings in a whole host of interesting questions. For example, in the context of reinforcement learning, how do we actually reward AI systems effectively? What should be the reward function that conveys our values and our desires? And given that the AI is going to optimize whatever it is that we provide. One of the big sort of important practical aspects is the interpretability of AI systems. Deep learning especially builds these systems that are a little bit hard to examine under a microscope to understand why exactly every computation turned out the way that it did, and to understand what the system is actually doing. However, at least in my opinion, it's not really interesting to look at the very micro level, at this level of neurons, to understand what the system is doing. Really what we want is to understand at a high level, what are these systems capable of, and to be able to debug them at a high level. This leads us to think about, for example, various ways of doing validation and certification of these systems that perhaps would be similar to the way that we certify the capability of people for carrying certain jobs. Maybe these systems will have to undergo a series of tests to understand, what are their error rates in real situations, to understand how to use them. And of course, we'll always have to have a person in the loop using the system, being able to correct the system, and being able really to step in if necessary. And so, for example, in all of the medical imaging applications that you have seen, while the performance in the papers is reported as accuracy of the system by itself, really in practical deployment, there's always a doctor, a radiologist there that looks at the predictions, analyzes them. And in some ways, what the AI is doing is just providing a different view of the data, perhaps an enhanced view of the data, but nonetheless, the ultimate decision lies with the person. There are many ethical implications of the use of AI systems that are of great debate in the community. There's been a lot of recent work that has happened. There's several interesting organizations that are emerging as leaders in this field. Montreal from the beginning has been a leader in this field through the Montreal Declaration on AI that was established in 2017, through a co-creation process that actually involved not just researchers, academics, and industry members, but actually also members of the society at large. And the new consultation is just launching this year again to understand the way that everybody thinks about AI and the way that they hope to use AI in order to ensure that the systems that are being built are actually built for the society that we live in. I will stop here. Thank you very much for your attention. And I would be happy to take some questions. And I know that we do have some questions that have come in before. Thank you.
We actually do have questions, Doina. Thank you for that wonderful presentation. I really enjoyed it. So the first question says that given that AIs are all logic and no emotion, they tend to resemble the minds of psychopaths slash sociopaths. How do we go about constructing AIs with artificial emotions and/or some systems of morality so that they can make proper decisions when controlling driverless vehicles, weapons, and other potentially dangerous devices?
That's a really interesting question, and one that actually comes up a lot. And so I will say a couple of things about it. First of all, I don't think we really want AIs necessarily to have emotions. Again, going back to the analogy, like, would you want a tractor that has emotions? It's not necessarily, very useful to have that. However, we would like, if AIs are deployed in our society, that they understand how our society works and that we can convey moral values to the AI system. And this is a topic that's actually quite a bit under work. Sometimes people call this the value alignment problem, aligning the incentives that are provided to an AI with the societal goals that we might have for this AI system. It's difficult, and it's difficult to do even for people, right? Like, how do we align all members of society to pull in one direction? Even the COVID epidemic is showing us that, people have different value systems and different personal situations and different interests. And so, we end up sometimes with social dilemmas. It's a very active area of research. The ethics in AI community, the algorithmic fairness community are all looking into this. There are, algorithmically, there are ways for us to convey what we value, right? For example, through reward functions. But what's the right reward function may actually be a matter for social debate rather than a matter for for the AI to figure out, right? Ultimately, an AI would need to be told what to do. And again, I emphasize the fact that we need to have people in the loop. One final thing that I want to say on this topic is that I'm really a firm believer in not having AI anywhere near weapons systems. And in fact, I co-signed with many other researchers a letter to Prime Minister Trudeau back in 2017, asking for the banning of AI technologies in weapon systems. And I still hope that will in fact happen.
Thank you for that lovely answer. This other person asked, what are the current challenges in using AI to answer our global energy concerns?
That's a very good question. So I didn't talk very much about AI as a tool for climate change, but actually I have a colleague, David Rolnick at McGill University, who's a new professor in computer science, who leads a global effort on the use of AI for sustainability and in sort of trying to prevent climate change. There are many applications that people are looking at. Some of them have to do with prediction, for example, predicting the impact of various interventions on the trajectory that we might have in climate change. Some of them are actually using technology like the generation of images in order to try and persuade people to be more mindful of climate change. So for example, I have some colleagues at Mila who are working on an application that would show you what your house would look like in 50 years if there's climate change, right? That maybe it would be all flooded or there would be no vegetation around and so on, just to sort of sensitize people to these issues. The part of the difficulty is, of course, AI needs data or it needs simulations that can produce useful data. And we only have so much data on climate at high resolutions. We are gathering much more high resolution data now, but historically, we've had fairly sparse measurements, right? Maybe precipitation and temperatures and so on over, say 150 years or so. And then really a lot of more sensing modalities have come online perhaps in the last couple of decades. And so, some of what people are trying to do is to understand how we can use this data efficiently, perhaps in combination, let's say, with physical models in order to sort of extract more information. And also there are some specific problems that can be targeted where AI can in fact be very effective, right? So for example, one could look at, let's say, forest fires in some particular part of BC, or one could look at the impact of deforestation in a certain part of Quebec on certain species of animals. Those are cases where perhaps we can build simulations and then train AIs in order to make good predictions more easily than at the global scale. But there's a lot of interest in this field. It's very interesting. It's interdisciplinary because a lot of the scientists that are involved have training perhaps in physics or in climate science and in AI. And it's a field that's really up and coming.
Thank you.
We have a new question, actually. How can we overcome this gap between data volume and data utilization?
So that's a very interesting question as well. And it, how much we can overcome this gap really depends on the field that we look at. And so, for example, in healthcare, we have a lot of data that's coming in because now everything is computerized. And so we have a lot of information sitting around in hospital IT systems and doctors' offices and so on. However, in healthcare, at least, it's actually very hard to put that data together in a meaningful way. And there's all kinds of reasons for this. Part of it is, of course, privacy. We need to respect privacy regulations. Part of it is sort of mundane computer science issues. The data might be in one format in one hospital and a different format in, let's say, the government data banks, and it might be in a different format at the pharmacy, and it needs to kind of all be glued together. And then, of course, there needs to be a will to make this data available to AI systems in order to learn predictions. And so in a field like healthcare, while the technical difficulties could be overcome by, for example, training systems to bridge the gap between these different IT databases, the regulatory framework needs to be in place for us to be able to access this data in a way that is, that complies with the law, but also that allows us to train systems that can actually discover interesting patterns in the data. In other cases, so for example, in manufacturing, the data, there's a lot of data that comes in because there's a lot of sensing capabilities now on modern manufacturing floors. So there's a deluge of data. And the question becomes, is there enough of an infrastructure to build in an AI system on top of that in order to be able to take advantage of this information to, let's say, improve the manufacturing process, or in order to understand how to order parts better, and so on. And so it's more a matter of actually the collaboration between the AI researchers and the people who are in that field to understand what are the needs and how to construct the infrastructure around the data so that the data can be utilized. There are some interesting initiatives in Canada in this respect. So for example, Scale AI is a network that was funded by the Canadian government that involves many industrial partners, as well as universities, that look specifically at these kinds of problems. So trying to put together companies with researchers to understand how to use this data that is being produced everywhere. Its emphasis is mainly on supply chains for Scale AI, but I can imagine that something like this could be done in other fields as well. So I think, in some cases it's a regulatory framework. In other cases, it's more a matter of actually being able to spend the time to understand what are the interesting applications that can be built, and to really work together. And this actually requires, quite a bit of adaptation, because of course AI researchers know their field very well, and they like to do the math and they like to do the programming, but they need to be able to talk to these people who are in industry. And likewise, people in industry need to understand just a little bit about the AI technologies in order to figure out what's their best use. And I think we're making progress in this direction as well, both through training as well as through some of these joint research programs.
Thank you.
I think this may be the last question we have given the time constraint. And this question is McGill a leader in the field of AI?
I would say definitely. And, you can look at various metrics, of course, to measure this. For example, this Canada CFAR AI Chair Program, which has, I believe, 24 researchers at McGill who are members of the program now, not just in the School of Computer Science, but also in Faculty of Medicine, the Faculty of Engineering, across many different departments. That's definitely a recognition of our strength in this field. And I hope that with the training programs that we have in place, we're going to continue, in fact, to be at the forefront of AI research. We are especially, recognized for reinforcement learning because, traditionally we've done a lot of this, but actually there's new emergent areas, especially at the intersection of AI and medicine, AI and neuroscience, as well as natural language processing, for example, where AI where McGill has really become very well established and very well recognized. And, we hope to continue on this route.
Thank you.
Well, thanks, Doina. On behalf of the ambassadors, Tiffany and Anthony, on behalf of all the participants who joined us, this was a live stream to YouTube. We do have gifts of appreciation. They will be sent to Doina. We have items that are from the Red Path Museum. There are 2 booklets to the Red Path Museum's galleries. One is the Fossil Gallery. It looks like Doina likes it. And the other is the Mineral Gallery. So these, even though the museum is closed, and this is actually the gallery that you go into to see the fossils, you will be able to enjoy a visit to the Red Path Doina. You will get it in the mail. Along with it, our bookmark, which is part of Darwin's letter. Darwin sent a letter in 1871 to the director of the Red Path Museum. He was acknowledging his contribution to the very early understanding of terrestrial vascular land plants that Dawson had found and described from the Gaspé area way back in 1870. The Darwin letter is, of course, at the Red Path, but you can go online, Google Darwin letter at the museum to learn about it. And finally, the other item, you get to have your own 3D stereoscope postcard that you will look in the back and it will expand and you will be there. It will seem as if you're there.
Yeah, I really look forward to being at the museum again. You know, my kids love the collection, and we've spent lots of time over the years in the Red Path. So we're looking forward to be in person there again. But in the meantime, this will be a very nice reminder.
I'm pleased that everyone has the Red Path in their hearts and in their lives still in some way. I go there once a week. I have the privilege of still working there. We're preparing Museum in a Box that we will have ready for the fall, a suite of these boxes to be loaned out because we cannot welcome people into the museum. Anyway, join us again in a month's time. This series continues. Our second speaker is Daryl Haggart from the McGill Space Institute. She'll be taking us into deep space, where she investigates the most extreme forms of astral phenomena, neutron stars, black holes, at the very perimeter of what we understand our space to be. That is May 13th, 6 o'clock it starts. There is no pre-registration. You just keep following these links. You Google in Mini-Science 2021 McGill, and it should pop up, and you will actually see the YouTube slide saver with Daryl's picture on it, the title of her presentation, and that's what you want to keep track of. We hope you've enjoyed being with us for the very first Mini-Science of 2021. Thank you to our behind the scenes, Fergus Grieve, Stuart McCombie, and once more, many, many generous people from the Trottier Family Foundation who've supported Mini-Science at McGill since 2009. I'll see you all in about a month.